And of course, we can stop when the thing offloads or whatever.
Okay.
It's all good. So yeah, so it's analytic everywhere except Z0, and the condition is that Z0 has to be a point for which
I think you were explaining what analytic meant before.
analytic means that you can represent the function by a Taylor series.
Okay.
And complex analytic. And it turns out that it is a sufficient condition for the complex derivative to exist at Z0, if I remember right. It turns, well, I'm going to get in trouble if I'm not careful. But anyway, here, without trying to recreate the whole complex analysis course here, essentially the point Z0 has to be a point where there exists a Laurent expansion.
Okay.
Right? It cannot be this theorem is not, it's true for functions that are analytic everywhere except like at one point where there's, it has a pole of order r, as it's called. The pole it's not an essential singularity. There's finitely many reciprocal terms in the Laurent expansion. Or another way to say it is that there exists a finite Laurent expansion. Finite, probably the word. There exists a Laurent expansion. Now, so you got to appreciate the weirdness of what this is saying. This is saying that you can calculate an integral around a closed loop by simply identifying the singularities of the function, verifying that the singularities aren't so nasty that they're like an essential singularity. Actually, those examples are kind of hard to come by, and in practice. And then all you gotta do is calculate the Laurent series, and that's the there you go. That's the integral. Yeah. So like you're like, well, okay. Well, do you have any examples of this? Yes, I've already shown you a couple. So my example one, we had the integral over the unit circle of like dz over z, right? Is 2 pi I. Well, in that case, f of z was 1 over z. That actually is already that is a Laurent expansion where it has a pole of order 1. The Taylor series part is 0.
Yeah.
And you just have b minus 1 equal to 1. So like the residue at z equals to 0 of 1 over z is just 1. So that is it. In contrast, if we have the integral of 1 over like z cubed or squared or whatever, that's equal to 0 because the residue of 1 over z squared at z equal to 0 is just 0 because there is no like 1 over z term.
Yeah. Because there is no 1 over z term at 0?
There's 1 over z squared,
Yeah.
but there's no 1 over z term.
Oh, okay.
Now, here, let me see if I can find a slightly more calculational. Oh, by the way, example 3, something that this fails for would be something like f of z equals to exponential of 1 over z. That has
z term.
That has z equals to 0 as an essential singularity. So like I'm saying that this is 0 for z equal to 0, and this is for z not equal to 0, the formula, right?
Yeah.
So in this context, if you expand exponential in its like series that has, it's got 1 over z, it's got 1 over z squared, it's got 1 over z cubed, it's got 1 over z to the 4th, it's endless. This has z equal to 0. Is essential singularity. So I'm trying to think if I can think of an example. I'll try to show you an example of something that's interesting. Let's see here. What if we looked at like the integral over the circle of radius 2, all right, of dz over z squared plus 1. So here we're looking at f of z is 1 over z squared plus 1, okay? Now that has two singularities. So it's got, because that factors into z minus I times z plus I.
Yep.
Alright. So let me make this circle a little bit different to make my life easier. I'm going to make the circle modulus of z minus I. He has been warned. Like, don't cut things with scissors. Now, so that is, this circle, right? And I want it to be counterclockwise. So there's I is in the middle of the circle, and then minus I is down here, right? So if I believe the residue theorem, the answer should be 2 pi I residue z equal to I of, f of z. So then the question is, how do you calculate the residue of things like that, right? So let's see here.
If you broke it down like you did below, wouldn't you say that, like here we said that, like with z equal to 0, the residue would be 1. Right there, z is equal to I. Right? You could break that up into 1 over z minus I times.
I have to write this as something like, some constant I'll call b minus 1 over z plus I plus b0 plus b1 times z plus I.
Mm-hmm.
I'm gonna just assume it starts here. I mean, that's an assumption, but I'm gonna say it can't be done. Now, so it's not obvious what happens with, and I meant minus I, I'm an idiot, because we're centered at I. Minus I. It's the old algebra thing. If you're looking at the 0 being 3, you have to look at x minus 3. It's that same thing. Okay. So, see, the thing that's calculationally non-trivial here is, what did I do with that? All right. And, I mean, there are various approaches. I'll show you.
Break them up and then evaluate one and then evaluate the other.
Well, it turns out that 1 over z plus I, this is in fact analytic. At z equals to z equal to I. Because you can plug in I, you get 1 over 2I. Essentially, that means the formula's nice. If the formula's nice, it means it's going to work out.
Yeah.
Now, so I could just do like Taylor's theorem, you know, but something like this, geometric series, is like super nice. So geometric, to make this geometric, I factor out an I, and then I'll have 1 plus z over I.
Factor out I. Yeah.
Ooh, but this is a poor choice because then I'm going to get powers of z. I don't want powers of z. I want powers of z minus I. So I got to be a little bit sneakier. A little bit sneakier than that. I need to, how did they say, be the change you want to see in the world or whatever. So, sorry, it's horrible, but anyway, what's done is done. So how about this is 2I plus z minus I. Because now I've got a z minus I. Hooray. I want to make that a 1, so I factor it out. The reason I want to make that a 1 is because then I can use geometric series. So I get a z minus I over 2.
2I.
2I. Thank you.
Okay.
And then at this point, I can go back and, you know, of course I can bring the 1 over 2I up front, up here, you know, if I like. You remember the old song and dance, 1 over A times 1 minus R is A plus AR plus AR squared plus, guess what, that's still true complex.
Okay.
So this is, you know, some, well, let me just write out the terms. This is 1 over 2I, 1 plus z minus I over 2I plus z minus I squared over 2I squared, and so forth and so on, right? So all I've been doing is I've been picking at how to deal with this factor right here, right? Like how do I expand 1 over z plus I? And I found out you do this, right? So all I gotta do is go back to the start and go, okay, so 1 over z squared plus 1 is in fact 1 over z minus I times what I just underlined in red, which is 1 over 2I times 1 plus z minus I over 2I plus z minus I squared over 2I squared, and so forth. I'm writing a little more than I need to here, all right? Okay, so now we have the Laurent expansion, see, because all you gotta do is just like multiply this out. You can see what it is. It's 1 over 2I divided by z minus I, right? Plus this times that, which you see those, that just gives me, these two cancel, and I get like 1 over, you know, 2I minus 4, okay? 2I minus squared.
Yeah.
And then the next thing I would get is, you know, plus 1 over, and I think I've neglected a sign here. This is supposed to be plus, it's supposed to be minus.
Are you factoring both in, or are you just factoring
So
2I?
the thing is, R here is z minus I over 2I. Well, excuse me, minus that. Because I have to have 1 minus R in the geometric series. So it's A, so it's like this minus that plus that minus and so on. So I have a minus here. And that matters because well, actually it doesn't matter. That ends up making this a plus 1/4. Actually, it doesn't matter at all. To the first term is actually what matters. But I'm just trying to stick with it here for a second. So then 1 over 2i cubed. So it goes plus. Well, the signage is complicated because the I squares gives you minus 1 to
Yeah.
Anyway, so I mean, not dragging this on too long here.
I think you can get away with it because the I on top and the I on bottom should cancel each other out. No, not
There's
necessarily.
more and more of them because you have higher and higher powers of R. But you got that fourplicity of the imaginary unit. It always comes back to like cycles of 4. You know. The point is, this is the Laurent expansion. So this piece is the Taylor part of the expansion. You know. And there you go. This is the singular piece. That's all that matters. So that shows me that the residue, this residue, right, is what?
The 1 over 2i over z minus I.
Yeah, it's 1 over, just accept 1 over 2i. So I get 2 pi I times 1 over 2i. So it turns out this integral is equal to pi.
Yep.
And you notice that I didn't actually do any integration.
Yeah.
Yeah. Now,
Would it be so? What are the problems that come with integrating it?
oh, well, I mean, that's
Like,
fine.
if we went like just straight.
Sure, we could do that. Let's look at it. We up here. So straight up, we've got a z minus I equal to 1. So that says I can look at the parameterization z equals to I plus e to the it. That is the natural counterclockwise orientation of the curve. I mean, parameterization of that curve. And we can do 0 to pi, 0 to 2 pi, right? So it's dz. It's I e to the it dt. The I differentiates to 0, you know, so as I look at this integral, I get, what do I get? I get the integral of I e to the it dt divided by z squared plus 1. Okay, z squared plus 1, so that's I plus e to the it, right? Squared plus 1. What is that, though? I don't know right offhand.
I'd break it up.
Yeah, I can work it out. So like I plus e to the it times that times itself, right? What's that work out to? It works out to minus 1 plus 2i e to the it plus e to the 2it. So notice that that's pretty cool because then the minus 1 I get from squaring and the minus 1 which is present in the f of z to start with, and that minus 1 we gone. Try to start using words, but you know those cancel, and so you got some kind of rather on its face kind of ugly looking imaginary exponential thing. And we got ourselves a 2 I e to the it plus e to the 2it, right? Alright, so pick your pi's in here. Oh, we could cancel.
Yeah, I'd break it up and then see if it simplifies because you get 1 over.
Yeah, we can. I mean, we can just like divide top and bottom by e to the it.
Yeah.
So we've got like I dt over 2I plus e to the it,
2 plus e to the it, right?
right? And that is equal to the integral from 0 to 2 pi of I dt over 2I plus cosine t plus I sine t.
Sorry, 1 second. Oh, you don't have the I. Oh, you don't have that. Okay, so you keep that I there.
Yeah.
And then you keep the I up top.
And I'll leave the I up top, but I'm going to have I times cosine t minus parentheses, well, minus I times parentheses 2 plus sine t, all right, divided by cosine squared t plus 2 plus sine t squared dt. So finally finishing low here, this is the integral of 2 plus sine t over cosine squared t plus 2 plus sine t quantity squared dt plus I times integral cosine t dt over cosine squared t plus parentheses 2 plus sine t quantity squared. And that is why you don't want to do it directly.
Yes.
However, check this out. Because this is equal to that. We know that this integral
Is 0.
0 to 2 pi. No, that one's pi, because that's the
Oh
red
yeah,
part.
this, yeah, that's pi, and the other place would be 0.
And this one's 0, right?
Yeah. Oh, okay. Or something. And that would be, should we assign something? Oh yeah, it should, yeah, okay, it should be, yeah, that actually, the left part wouldn't be too bad to integrate.
I mean, you do get a cosine square plus sine square,
Yeah,
so then you get a
like a 2 pi, 2 sine t.
it's 5 plus 4 sine t or something.
Yeah,
But it's, yeah, I mean, it's not trivial. I mean, it's,
yeah. But this is a lot faster, yes, I will say.
so, this is actually one of the things you could teach in complex analysis is like, given a rational function of sine and cosine, you can take that integral, and you can convert it from 0 to 2 pi, and you can convert it to a corresponding integral over the unit circle of a particular complex function. It's kind of a sneaky way to do integrals of rational functions of sine and cosine. That's just kind of a quirky application. But this thing I'm showing you, this is called the residue calculus. It actually allows you to do all manner of integrations, which you have to be a real calculus ninja in the real case to do. I mean, I think once you find a closed form formula by some technique, you can find it by another, you know? But I think there are a lot of integrals that are accessible from the complex technique that are quite difficult otherwise. And the, let's see here. Okay, let me just expand on this example just a bit more, and then I'll stop talking about complex integration for today, okay? Now, the thing that we typically do in complex analysis is we like to use this. I mean, this is fine, nothing wrong. But what's perhaps more interesting is that this technique allows you to calculate infinite integrals in kind of a sneaky way, and here's how it's done. So for one thing, if you have a function which is analytic everywhere except at z, if it's analytic everywhere except z naught, and suppose it continues, well that means that you could morph this curve out as long as you don't hit another singularity. It doesn't change the integral.
Oh yeah.
So there's like this tremendous freedom of deformation. And so the practical application of that comment is for this one, right, I could just as well kind of stretch it out and go, I'm going to look at this integral. So I'm going to go over here to r, go over here to minus r, and this will be the circle, you know, z equals r e to the it, 0 less than or equal to t less than or equal to pi, all right? And as long as r is greater than, you know, let's say 2, just to be safe.
Yeah.
That's a nice one. I mean, you could make it bigger if you wanted. Then certainly I is going to be in here somewhere, right?
Yep.
So the calculation we just went through, still legit. If I call the curve gamma, it's minus r to r, unioned with the circle of radius r. And by it's really a half circle, fine. I'll put a plus here, just to say it's the upper half, all right? Right? So I'm saying gamma is it's the concatenation of this and then that, right?
Yeah.
So on this one, we straight up have, well, I can say it this way. On this one we have z equals to t. That's the parameterization of it. Over here we have z equals to r e to the it, right?
Yep.
So like here you got dz is dt. Over here you got dz as well. That same song and dance we just went through. Okay, great. And technically I should use a different t, right? Whatever. Fine. Here, I'll fix it. Ow. There, look. No danger for confusion now. Ah. Okay, so here it is. And I should call this gamma sub r because it's got an r dependence. So the integral over gamma sub r of dz over z squared plus 1 is equal to pi. Right? But it's also equal to the integral from minus r to r, right? Well, dz is d tau. Z equal to tau squared plus 1. So that's the integral over this guy. See? The integral over that piece. And then plus the integral from 0 to pi of r I e to the I t dt over r e to the I t squared plus 1.
Yeah, because we have and then the imaginary.
So consider the function, you know, g of t equal to r e to the it over r squared e to the 2it plus 1, right?
Yeah. You drop a R. No, you can't.
I dropped an I,
Yeah.
but whatever. So, I mean, really only the modulus of this anyway, okay?
Yeah.
So, that goes away. I think the modulus of the I is gone.
Could you pull out a could you pull out a r e to the it out of both terms, making it 1 over the r, and so I don't know, that kind of make it more messy. I don't know.
Let's see here. Let's just, for the sake of brevity here, I'll just write it out in real notation. This is I'm gonna get rid of the I because it just gets eaten by the modulus, right? But this is cosine t plus I sine t, right? Divided by r squared cosine 2t plus I sine 2t plus 1, right? So, what's the modulus of, so I'm assuming r is a positive constant here, right?
Yeah.
So like, I can pull this like that. Now, that is modulus 1.
Yeah.
So this is,
That's modulus 2. Sort of.
well, I don't know. I mean, we've got r squared cosine of 2t plus 1, right?
Yeah.
Plus I r squared sine 2t, you know?
Denominator plus 1.
Yeah, we got that plus 1 there. So
I see.
you can't just, I mean, it's not nice. However,
Ooh, no, there's a doubling formula you could use.
so what I actually want to find is a bound on this.
Okay.
Because I actually want to, this g of t really is f of, you know, f of r e to the it for this piece, you know?
Yeah.
So I'm trying to find, actually, the modulus of it. I'm trying to bound that.
Yeah.
I want to use the ML for that.
Oh, yeah, yeah.
That's what I'm after, actually. And so I want to find something larger than that. So,
Why don't we take the next up circle?
next up, well, I'm trying to like that, but if you think about this term and this term together,
Yeah, that gives you the circle.
Mommy didn't see it. She didn't see me yet because there was a table one. Because there was a table B. That's why Mommy said no.
Mom found something that you can cut? Is that what you're telling me?
Yes,
She said you can cut that one. But you gotta ask permission, right?
I'm ready.
Already did, okay.
So. So
Yeah,
it'd be, so e to the it is also equal to cosine t plus I sine t, right?
Right.
So could I say that e to the 2it, like r squared e to the 2 sine t plus 1?
Oh yeah, that's what I did here.
Okay.
That is that.
Never mind.
Fine. Listen, so it's like, this is one of those things that you learn in the course, but basically this will replace with less than or equal to, I want to say r squared minus 1.
I want to cut this.
You get that from where?
Well, if you think about these two terms, like what can make the modulus of this biggest is, excuse me, what can make them, excuse me, inequality logic, so we're trying to make a fraction larger,
Yeah.
right? So that means we want to make the denominator as small as possible.
Mm-hmm.
So to make the denominator as small as possible,
Divided by anything less than 1. I mean, greater than 1.
let's see. Let me try. See if I'm right about this. Just try plugging in some values. I'm kind of stuck in the other kind of thinking at the moment. What if I plug in 0?
Cosine 1, sine 0.
I get so I get r squared plus 1, right?
Yeah. If you plug in 2 pi or pi.
So that is definitely greater than r squared minus 1, right?
Yes.
Good. What if we put t equal to, you say pi?
Yeah.
Maybe, how about pi over 4, maybe? That's kind of the opposite story. Because pi over 4 makes this pi over 2, plus pi over 2 0.
Yeah.
So we get 1 plus, ir squared,
Yeah.
modulus of that. And that is, again, I guess technically that's square root of that,
Yeah. Maybe less than.
Oh, it's squared. I'm
1 plus ir squared would be.
I should maybe.
That should be less than r squared minus 1. Because the I makes it negative, and if r squared's over 1.
Well, technically this is 1 plus r to the 4th, actually. I think I might be missing Oh, I'm sorry, Audric. I have been away from this calculation for a little while, and like we use a particular variant of the triangle inequality here to make the denominator smaller. But it amounts to just, and you end up with this, but I might need a square root. The thing that's throwing me off a little bit here is that I've got an r squared downstairs.
Yeah.
So I feel like maybe I should have r to the 4th square root, or something like that, maybe. All right, let me not belabor these details here. I want to get to the point. Okay, so the point is, you can find a bound on this integram. Over the upper half circle, right? So like that's my m. So I can erase this.
Yeah. So.
Erase the offending part. I think there's something wrong in there. Anyway, the point is, this integral from 0 to pi of r e to the it dt over r e to the it squared. And I'm sorry, I don't have my ducks in a row here today, but for this piece, less than or equal to that bounding thing, which I do believe. I want to say 1 over r squared minus 1 is fine. I could be wrong, but I do think that r over. Goodness gracious. Golly. Man. Just a second. See, this is why I need to teach complex analysis. I am getting too far away from these calculations.
You okay, Benjamin? You want help? No, you got it.
She's doing Benjamin.
Trying really hard, that's for sure.
Now this.
Okay, Benjamin, what other options do you think you have besides pressing as hard as you can? Oh, you're twisted now. Okay.
This. Ooh.
We're gonna glue it. Yes.
Then
This problem should be pretty easy for me to find in the my old what's the word here? Complex variables course work. Like I should be able to find. Alright, so it's all based on using this. Audric, it's the modulus of z plus w is greater than or equal to the absolute value of the modulus of z minus the modulus of w.
Okay.
So that's the critical identity which I am
Okay, so
lazily not taking advantage of. So we're looking at 1 over z squared plus 1 modulus of z equal to this has modulus of z equal to r, right? So I can make the denominator smaller, which makes this larger.
yeah,
So I trade that for
modulus z
modulus of z squared minus modulus of 1, the absolute value.
Yep.
Now, modulus of z squared, like modulus of z squared is modulus of z squared.
Yeah.
So that's r squared.
Yeah.
And so that's why I get 1 over r squared minus 1.
Okay.
That is what was bothering me. Was I was running into this r here. It's because I'm foolishly trying to bound the formula for the integration, the complex integration. I shouldn't be doing that.
Yeah.
I should be trying to bound the complex function, because the ML theorem says you find a bound on f of z,
Yeah.
and then that's m. So sorry.
Okay.
So, long story short here, this piece, which I'm going to rewrite more productively as, instead of integral from 0 to pi, I'm going to write that as the integral over CR plus, all right, of 1 over z squared plus 1 dz, all right? So the point is, this is, well, the modulus of this piece, right? Is less than the length of CR plus, right? But the length of CR plus, that's easy. Length of CR plus is half circle. So it's pi r.
Yep.
So we've got pi r divided by r squared minus 1. There we go. So that's how we can bound that integral. Sorry to be so muddled a second ago. Like, I'm not an idiot. I'm trying to. I'm not using the ML theorem. I'm like, uh-oh.
Nothing.
Take it back.
Nothing just come in. It is an L socket.
Okay.
Not like that.
That's good.
No, don't worry. I'm still wrapping my head around a couple things, so it's okay.
So, okay. That is a bound on the modulus of this piece.
Yeah.
All right. So we know this is pi. Get this, get that. Now what we do, kind of
Yeah.
erase this. So thus, the limit as r goes to infinity of the integral from minus r to r of d tau over tau squared plus 1 is equal to, well, pi minus the limit as r goes to infinity of pi r over r squared minus 1. Maybe that's not the right way to say it, but I mean...
Yeah, because I thought we got that it was pi. What do we get from the other thing?
Well, I would just say it this way. I don't have to write that there. As r goes to infinity, what happens to pi r over r squared minus 1?
Pi r over r squared minus 1 as r goes to infinity. Well, it's 1 over, essentially it's 1 over r. When you get down to it, it gets smaller.
Mm-hmm.
Yeah.
So this piece in that limit goes to 0.
Yeah.
And
So you just left the pi.
This
That's what
thing
we
come off.
got earlier, right?
This
So-
thing come off. I put this off.
so therefore,
Wookie,
integral from minus
wookie,
infinity,
wookie.
wookie, yes. Okay. Now, if you're a good calculus 2 student, you should be like, and,
I
Oh,
did it again.
oh no, there's no plus c here, it's a definite integral, but you should be like, well, a couple things. Number one, the integral from minus infinity to infinity is not defined in terms of a symmetric limit. Like you have to take limit to infinity and minus infinity separately and distinctly.
Okay.
So technically speaking, what this calculation does is it shows you that the principal value of this integral is pi. But it so happens that the integral exists, so the principal value is equal to the integral. I mean, there are integrals which have a principal value of 0 and yet they diverge. So, because the principal value is defined to be like the limit as the bounds symmetrically go to infinity, whereas the actual double integral to infinity doesn't assume any connection between the positive and negative infinity bounds. That's just the definition. But now, the real reason I'm not so much fussing about that. I'm more fussing that, well, we already know how to do this integral. This is an easy integral, right?
Yeah.
The integral of, d tau over 1 tau squared plus 1, well, that's inverse tangent of tau, right? And so if you go to infinity, you go to pi over 2. And if you go to minus infinity, you go to minus pi over 2. So pi over 2 minus pi over minus pi over 2 gives you pi. So it's completely unsurprising.
Yeah, but we had to prove that the imaginary piece
I'm
goes to 0.
drawing.
But this same technique can be used to calculate much uglier integrals. So I mean, this is a relatively simple example because it's a complex calculation of what's also an easy real integral. And so this example's kind of easy in either scenario. And by the way, the whole calculation I went through to find the residue, there's like a way easier way to do this. When you study complex analysis, you get these like fundamental lemmas to calculate residues that shortcut much of these calculations. So I showed you a way to understand it in terms of, calculus 2 style calculations, but there are better things you learn in complex analysis. So anyway, that in a nutshell is why complex integration is interesting, because it allows us to solve real integrals in new ways, and also just the actual theorems of complex integral calculus are very, very interesting because there's a link between differentiation and integration. So Koshi's integral theorem. I should write that down for you. Let me find it. Because that's essentially the thing that separates, in my view, it separates complex analysis from integral A calculus. Integral A calculus doesn't necessarily have a generalized Koshi integral theorem. A generalized Koshi integral theorem. Let's see if I can find it here. All right, here's like the simplest version of this thing. if you have a bounded domain with a piecewise smooth boundary, Benjamin, buddy, you can't make so much noise right on the table, okay?
I'm making
Well, you can make that, but just don't make it right on the table because it's super loud. Ooh, that would be good. I mean, we like having you here, Benjamin, but you gotta be quiet if you're gonna be here. So if f of z is holomorphic with continuous, oh, I was supposed to write. I guess we already. So if f of z is holomorphic with continuous f prime of z. Now that is a holdover of my notes from Gamelin. Actually, that's kind of redundant. On D.
This is the Koshi remote integral theorem?
And yeah, extend continuously to the boundary of D. So I'll tell you more. Specifically, this is from my theorem, section 4.4, called the Koshi integral formula. What I call guide to Gamelin. It's my complex analysis notes from yesteryear. Like the most, I sent you links to the course from more than a calculus. That's a different. That was different. So before that, I wrote notes which were parallel Gamelin's complex analysis, and in those notes on page 91, I guess. I state Koshi's integral formula, and I'll just get to it. Koshi's integral formula, and you can find this in pretty much any complex analysis, but Koshi integral formula. It says f of z is equal to the integral. Well, excuse me, 1 over 2 pi I. The integral of the boundary of D, f of w over w minus z dw.
That's partial D right there?
Yeah, the boundary of the domain. A domain is an open and connected set in complex analysis.
And this is, are we talking about, this is in the term of the complex, right? So how do we take this theorem and morph it over to any algebra?
We don't. And also this as a consequence, the nth derivative of z is the 1 over, this is Cauchy's generalized integral formula.
Okay.
The nth derivative of z is m factorial over 2 pi I. Integral of f of w over w minus z to the m plus 1. This is Cauchy's generalized integral formula. Now, it may not be apparent from first glance that this is the same as the residue theorem stuff, but it is. I don't think it's at all obvious, honestly. So the Cauchy integral formula says that the value of the complex function, right, at z is equal to the integral of the values of the function on some curve around Z.
One more time.
You have to appreciate the weirdness of, alright, I'll make a picture. So like here's D, alright? And here somewhere is Z, alright? The boundary of D is this, the exterior, right?
Mm-hmm.
This formula says that the value of the complex function at Z, it's 1 over 2 pi I times the integral of the function divided by W minus C over the edge.
Is 1 over 2 pi I.
Formula.
Is 1 over 2 pi I times the integral.
Yeah, and then that says that the derivative of the function at Z is given by integrating the function divided by W minus Z to the M plus 1. So like,
Oh, these are primes. Okay. I
yeah,
thought, okay,
yeah. So
okay, gotcha.
this is M equals to 0.
Yeah. Gotcha. I was tricked for a second. Okay. Yeah. Okay. So the value of the function at that point Z is simply 1 over 2 pi I times the integral of that. And what the general was stating is that you could find the value at that point Z, or the derivative of the value of the point Z, by doing the factorial of how many derivatives you take.
And doing that integral.
Yeah. Okay.
I mean, to me, these are very weird formulas when you first see them. I mean,
Yeah.
very strange formulas, but they, you use these.
I'd like to see them derived at some point, but I'll take the word for them.
Oh, when I teach, if and when I teach you complex analysis, I'll drive them there.
Okay.
So the proof, like so many things, rests on a combination of like basic lemmas, and then I think there are a couple different ways to go at it, but one way it basically ends up being geometric series, or there's an induction. I got an induction hypothesis argument. But you notice that you can solve that Cauchy's generalized integral formula
Mm-hmm.
for the integral is equal to 2 pi I times the nth derivative divided by m factorial.
Yeah.
And you can see why that starts to resemble the residue calculus, but it's not.
Yeah, I see like the 2 pi I part.
Yeah. All right, so yeah. So there you go. There's 6 weeks of complex analysis condensed into 2 hours. So those kind of the high points. So one of the things that you get from things you get from Cauchy's generalized integral formula is like you can't have a complex function on an open set which is just like once complex differentiable. All right. Suppose you have a complex function such that f prime of z exists continuously on some open set. Well, then you can calculate f prime